Abu Bakr, late. Why? Very bad. अभी आ रहे ना बेटा तो तुम you have to be good yourself. Why do you worry about others? Tell me this. Okay, so today we are gonna start with the electric fields. अच्छा अच्छा चलो कोई बात नहीं, it's okay. It's all right. Class के बाद you can enjoy the rain. अच्छा, so for electric fields, I just wanna basically tell you that it's a region where a charge feels a force. This force that I'm talking about can be attractive, and this force can be repulsive as well. Right, kids? Now, whenever you have a positive charge, it's isolated charge, the field basically seems like it originates through a single point, and that single point, this is why it is called a point charge. Same goes for this one. A negative charge would have a field directed towards a single point. That's why it is called a negative point charge. Now, so we need to understand why these lines go out from go out from positive and go in from negative, because direction of the electric field depicts the direction of force on a stationary positive unit charge. Which means is that if you place a unit charge here, it's gonna feel a force away from it, so it's gonna get repelled. That's why the field is out. And if you place a positive charge here, it's gonna get attracted towards it. That's why the field is towards a particular point. Now, kids, speaking of that, we then need to understand what exactly is electric field strength. Now, electric field strength is defined as force per unit positive charge. The symbol of electric field strength is capital E. Its SI units are Newton per coulomb, and it is a vector quantity because it has a particular direction. That's why. Generally, if you look at the definition, according to that, electric field strength is given by force per unit charge. That's how this looks like. Please write this down. All right, kids. Zainab late, very bad. Now, kids, done writing. Should I go forward, please? Okay. The next thing we got to look at is the uniform electric field. Now, in a uniform electric field, you guys should understand that number one, that all lines between the plates are straight. Number two, they are all equally placed. Sorry, in fact, let's write equally spaced. Number three, it basically means that constant electric field strength at all points within the field. So it goes like this, 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 like that. Same goes for this one. It goes from positive to negative, like that. Now, we need to understand few more things about it. So let's write a note here. The field lines always enter and exit the surface at 90 degrees. The strength of electric field is shown by the density of lines, like that. So this means that because the lines are closer to this one, so this one has a greater value of E compared to the other one, right? Is it clear, kids? Any questions? Please let me know. Zainab, you understand everything? Abu Bakr, Fatija? Okay, very good. Write it down, please. All right, kids. Now we got to go to the next. Right. Now going to the next, we're going to look at analyzing uniform electric field. Now, when you look at electric field, we can find its potential difference by putting a voltmeter across the plates. And then let's suppose its diameter is, sorry, the distance between the plates is d8 centimeter. And this is 20 volts and this is minus 20 volts. So basically, right where you have plus 20 volts, this is the 0 point. And then it would show you a straight line, and this straight line will go till minus 20 because you reach the other plate, and exactly in the middle you will have 4 centimeters, because right in the middle here you have no potential because it goes from positive, decreases to 0, and then to the negative value. So you guys need to understand that. The other thing you guys need to understand, that when you find the gradient of this, so the gradient of this line will give you negative change in voltage over change in distance, and the gradient of this line basically shows you the electric field strength. Hence we would learn from this point that actually electric field strength, Samir late, very bad, electric field strength is also known as the negative potential gradient. This is what you should always remember. This is another definition of electric field. Now, the point is, how did I get, like, how can this be a possibility? Because why is electric field strength V upon D? We're going to derive that formula right here. So write a derivation here. And the derivation is that electric field strength is given by force per unit charge, as we studied just now. Now, obviously, whenever you place a charge, it will feel a force because of the electric field, and that force is constant. So we can say that because force times displacement is equal to work done, let's call this W. So what we can do is we can put work done over distance moved equals to force. We're going to replace this from this one. This will give us work done over Q times T. Now, the next formula we should remember is that work done itself is voltage times charge. So I'm going to replace work done as well. This will be voltage times charge over Q times T. Q and Q will cancel out. Ultimately, you will get another formula of electric field strength, which is potential difference over the distance, like that. If you couldn't understand this, please let me know. Okay. Yes. Samir, Zainab, Abu Bakr, Khatija, everything is clear? Very good. Samir, wake up, please.
जी जी
Where were you, Samir? Sleeping?
नहीं सर यहाँ बारिश हो रही है सॉरी
तुम भी अबू बकर के तो नहीं इस तरह रहते नेबरहुड में कहीं?
पता नहीं सर
Okay. Abu Bakr, probably he lives next door. He doesn't know you. Sad. So now So now, basically, I want you to go look at. Acha, theek hai, that's good. So we're gonna look at this part. This one I'm going to give you as homework because it just means what is electric potential. We are basically going to do electric potential later, so this is homework for later. But for now, let's look at this question. In this question, they have given you a point P, and they said that plate A is Earth. When something is Earth, it's at zero potential, and plate B is at V naught potential positive. It says point P situation is center region where the plates at distance x. Now show the variation. Now the moment you see this, all you need to do is again the same kind of diagram, but this is basically a clever one because they haven't given you the negative side of the potential because it basically ends at zero. So this D has to be this D because the other plate was zero. So it will be a straight line. The reason why it is a straight line because it is a uniform field within it. And the other thing is that the distance from that potential to zero is just t. That's fine. All right, kids. Any questions? Please let me know. Very nice. Very nice, kids. All right, kids. Now let's have a look at the next. The next thing we're gonna look for this is the acceleration in an electric field. So let's check it out. Electric field strength is given by force per unit charge, and force is equal to ma. Now, we can put this back here. This will become electric field strength equals to ma over q. Because you need the acceleration, you can make it the subject, and it will be then eq over m, like that. Very simple like that. Now you can see what these are. So this is obviously electric field strength. This would be the charge. This would be the mass. And that's the acceleration. Just like that. Okay. Quickly write this so we can go forward. If you have any questions, let me know. All right, kids. So now let's go to the next. So the next thing we're going to look at is the Coulomb's law, and this is where A2 starts from. And about Coulomb's law, this definition, this law will be of 2 marks. The first mark you're going to get when you write the force of attraction or repulsion between two charges is directly proportional to the product of their charge. Then the other point you're going to get is when you write and it is inversely proportional to the square of distance between their centers. Now, once you've written this, what it means is that the force that two charges experience is proportional to product of their charge, and it is inversely proportional to the square of distance between their centers, and this is also called the inverse square law. Let's suppose these charges, one is positive, one is negative, doesn't matter what kind of these are, they're going to attract each other with the equal force, and this force can be found out by a simple formula, which is F equals to K Q1 Q2 over R square. This F is then equal to, basically can also be written as Q1 Q2 over 4 pi epsilon times R square. Now please understand that this K that I'm talking about is called the electrostatic constant. It is not a real constant, it is just derived from 4 pi epsilon. Its value is 8.99 times 10 raised to 9 Newton meter square coulombs minus 2. Whereas K itself basically belongs to 4 pi epsilon, like that, 1 upon 4 pi epsilon, where this epsilon is called the permittivity of free space, which is 8.85 times 10 raised to power negative 12 meter minus 3 kg minus 1 second 4 ampere 2. This is not relevant to basically remember the units. The values are given as well in your data booklets. So yeah, it's pretty good that way. Okay, that's pretty bad. If you have any questions now, please let me know. Okay. Okay, that's good. All right, kids. Now we're going to look at the derivation of electric field strength with respect to a non-uniform field like this one. So let's check it out. The first thing that we learned initially was that electric field strength was force per unit charge, and then we learned that force is equal to KQQ over R square. You can write Q1, Q2, or capital Q, small q, it's the same thing. Now, what you are do is, you know that this can be written as F equals to EQ. So I can put F equals F, so EQ on this side, and KQQ over R square on this side. Q and Q will cancel out. So E will become equal to kq over r square, or we can also write it as E equals to 1 upon 4 pi epsilon times q over r square. Whatever formula you like more, you can stick to that. Now remember that this is a vector quantity, hence the negative and positive signs show you the direction. That's important in vectors. You got to remember that as well. All right, kids. Done. Should I go forward, please? Zainab, Samir, Abu Bakr, Khatija, everything is clear?
जी सर.
Okay. Good, 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 good. All right. Now let's check out this question, okay? Now, in this question, it says that state Coulomb's law. I'm going to give you this as homework because we have just done it, and it's better that you complete this part. But we're going to look at this part, which is right here, and that's going to help us build some confidence in going forward. Now, this question, I believe, came in probably 2023, February, March. So this is the most latest one, last year one. It says the charged sphere X is supported on an insulating stand. A second charged sphere Y is suspended by the insulated string. Okay. So that the Y is in equilibrium, and the charge on X is 96, as you can see, and charge on Y is 64. So whenever you're using, you're reading through it, always mark the important details. Length of thread is this one right here, which is good. And the distance between them is this one. Fair enough. Now they say that on figure drawn label all the forces acting on force Y. Obviously, this object sphere will have some weight. So the weight is going to be right here. I'm going to write weight. Then it is why it is being repelled, because this must have a force acting towards the horizontal, and it is the force of repulsion. And then because string is basically balancing all of this, so it's being pulled. So the pulling force has to be the tension. Is it clear, kids? Some of the AS things will be here, so please be ready. Okay. Okay, kids. Now it says determine the mass of the sphere, because you see, the thing is that if you look at the whole diagram, you see we can find the forces, but for that, obviously, to find the mass, we got to have an idea about the tension. It's a full 4 mark question, so let's try and do this together and see what you got to do. First of all, I'm going to draw the triangle for this. So if you look at this, initially, the triangle would be like that. If you notice, this length is given as 1.2. This separation is 0.080. And we got to find this angle because actually we need this angle to find the components of the tension. So this angle would be this one. We want to find this, right? So it's pretty simple. This is 90 degrees. I know that it's going to be sine. So sine theta is going to be perpendicular over hypotenuse, like that. Get it, kids? So let's find the sine. It's going to be something like shift sine and 0.08 divided by 1.2, and this will be 3.82 degrees. Now I have the angle is next to it, so this will be tension sine theta, sorry, cosine theta, and this will be tension sine theta, like that. Now because it is balanced, which means in equilibrium, tension sine theta should be equal to the force of repulsion, and weight should be equal to tension cosine theta because it is all balanced. Now what to do next? We got to find this tension in order to find the weight, right, kids? So it's pretty easy now. All you need to do is you need to write T sine of 3.82 equals to 8 point. So I'm going to use K Q over R squared. So for that, T sine 3.82 equals to 8.99 times 10 raised to power 9. The charge on the first one was 96, the other one's 64. So let's do 96 into 10 raised to power negative 9, it's nano, into 64 into 10 raised to power negative 9, divided by their separation is this one, 0.080 whole squared. Now simply just try to find this. And then divide it by this. So your answer should be 0.00863. Now we got to find tension. So we got to divide this by sine of 3.82. So let's do that. Answer divided by sine of 3.82. So I'm getting a tension of 0.1295. I'm taking more number of decimal places right now just to, round it at the end. Sometimes if you take, you round it in the middle, what happens is that you lose the correct significant figures in the long process. So you don't want to do that. So now that we have tension, so we're going to take it here. Let's solve it with a different color. So W is equal to mg. This will be 0.1925 cosine of 3.82. And to find the mass, we need to divide the whole thing by 9.81. Let's do this. So this answer multiplied by cosine of 3.82 divided by 9.81. So I'm getting a mass of 0.013 kilograms. Now you need to be very, very careful that you give your answer in the correct significant figures because sometimes what it happens is that If you don't give it in the correct significant figures, you will not get 1 mark out of it because all the data was in two significant figures. So that's why we need to give the answer in two or at maximum three significant figures. Is it clear, kids? Please have a look at it. Let me know if you have a question here. Okay, that's very nice. All right, kids. Now that we have done this, we got to move to the next and says calculate the total electric potential at this point. Now, for electric potential, we have just learned a couple of things and says calculate the total electric potential. Oh, but I think for this one, we have to wait till we have done electric potential. So this will be homework for later. So please mark it so you can complete it later. All right, kids. Then the next part is about uniform electric field. So let's check it out now. So in this one, it says electron enters in the region between two parallel plates P and Q, and that are separated by a distance of 18. So this is clearly D, and we got to find the potential difference across these two plates. So this is Earth. Earth is always at 0. So 250 minus 0 is going to be 250 volts here. Now it says state the direction of electric force on the electron between the plates. Obviously, the electric field is going to be down. It always goes from higher potential to a lower potential, which basically means that the the electron is going to get attracted upwards. So the force on electron will be upwards. So we're going to write upwards. Then it says determine the magnitude of the force acting on the electron due to electric field. Now, obviously, we have understood one thing that to find the force, we got to use electric field strength into charge because electric field strength is force per unit charge, but we do not have electric field strength. We do have charge and electrons. So to find the electric field strength, we got to do V over D. Why is this? Because this is the formula that gives you the electric field strength between two parallel plates. That's pretty simple. The potential difference is 250. The distance is 18 millimeters. So I'm going to change it to meters. First, find electric field strength. So kids, this is about 1388.9 volts per meter. Now we got to find the force. We're going to add this right here. 1388.9 times the charge in electron is 1.6 times 10 raised to minus 19. So that gives us a value of force as 2.2 times 10 raised to power minus 15 newtons. And that's how I'm going to do this. Any questions, kids? Anything you'd like to ask? Khatija, everything's clear? Abu Bakr, Zainab, Samir? Basically, these things are new for you because they will be asked, like there are a few exams that have happened about it. So you got to be careful about that. Very good. Finally, they say why the electron does not follow a circular path. It's pretty easy. If the electron is moving this way, it doesn't follow a circular path because like they're saying it doesn't go like that. Why? Okay, it doesn't follow that circular path, although the force is up. The only possibility for this one is that you're looking at it from the top. So if you look at something from the top, in reality, if these were the plates, let me show you the diagram. And the electron must be going like this towards one plate. But then if you look at from something like this part, you would see that electron is going there, although it will be moving. In reality, it is moving up in the 3D space. So we would say that actually it doesn't go in the circular path because the force is perpendicular. Force, in fact, we'll write force is always in the same direction, whereas the direction of electron would be changing. That's what you were right. Any questions, please let me know. All right, kids, very, very nice, very, very nice. Write it down, please. Okay, now let's go to the next now. So the next thing we got to do is the electric potential. Now, electric potential will always be of 2 marks as well. So please see what 2 marks you're going to get. First mark will be given to you when you write work done per unit positive charge. Number two, in moving this charge from infinity to a point within the field, like that. Electric potential is a scalar quantity, and the SI units for electric potential are joules per coulomb or volts. I'm sorry. Now, electric potential is defined as work done per unit charge, like that. So you guys need to remember that. Now, for electric potential, we can also find electric potential in non-uniform field. So how do you do this? It's pretty simple. Let's check it out. As you can see from this thing, this is work done, and this is charge. So since we know that work done is force times the distance, so we can also say electric potential is force times the distance divided by charge, like that. Now we also know that F is equal to KQQ over R squared, so we can put this F right here. And when we do, it's going to be KQQ over R squared times R divided by Q. R and square is going to cancel out, Q and small q's are going to cancel out. So ultimately, you're going to get V equals to KQ over R, and this is the formula that is commonly used in all of the questions, almost all of the questions. All right, kids, any questions, please let me know. All right. Please write this down. Hmm. Okay, kids. Now, the next thing we got to do is basically understanding that, yeah, understanding what is the null point. Now, oh, by the way, before we go to null point, there's few things that I want to basically write here. So you can put a note here, please. Always remember that charges move from higher potential to lower. The other thing you guys need to understand is that we can earth to make potential 0. And then we shall go to the null point actually. All right, kids. Now, let's go to the next. So about the null point then. Oh my God, that's not fair. Okay. About the null point, I want to basically explain this to you. Null point is defined as a point where net, let me just write it in capital so you guys don't forget this word. This is a key word. Net electric field strength, which is basically a vector quantity, is 0. And remember that this is only possible between two like charges. Within this point, there are three things you guys need to remember. Note. Obviously, net electric field strength is 0. Net electric force is 0. And number 3, net electric potential is maximum. We're going to look at it when we're going to look at the third point when we basically do the other thing. All right. When we start the electric field questions, electric potential questions. My bad. Okay. Is that write it down, please? Okay. Going to the next then. Now going to the next, which is the potential graphs. Now this is very important. You're going to at least do this today so that you guys have no issues later on. First of all, if you have a positive charge, obviously it will have maximum positive potential as you go about it. To the right side, the potential is going to decrease because you're going away from this. And when you're reaching the negative, so it's going to get more and more negative. So the potential in the negative region increases like that. If you combine these together, let me just draw it with a different color. Huh? If you combine these together, basically it looks like something like this. The green side, and then after 0 becomes negative, like that. So this is the net graph for this. And as you can see, that no matter what you do, you create a tangent here, you create a tangent here, or here. Basically, the gradient at all points is not equal to 0, which means that electric field strength will be the negative potential gradient in this, and you can find it through all this. The potential never, the electric field strength never becomes 0 at any point. All right, kids. Any question in this, please let me know. Now, please draw this quickly so I can move to the next. Samir, everything is clear. Zainab, Abu Bakr, Khatija, any questions, please let me know. Okay, good. Now, in the next one, if you look at this one, both are positive. If you see both positives, what you see is as you go away from basically the first positive, it becomes like less and less positive, so it goes down. And as you go near another positive, the potential again increases like that. Because of this, basically the potential then, okay, let me just draw it with different color so I can see, I can show you. So the green line or the first one goes like that. The blue one goes like this. That's not fair. Now, when they combine together, they give you the net potential like this because they add up, right? The potential is maximized. Anyway, just in the middle, as you can see, there's no field that exists. So at this point, you see a null point. And why is it a null point? Because I told you at this point, electric field strength is 0. And how do we know? Because if I draw a tangent right here, it's a horizontal flat line, which basically means that at this point, the gradient is 0, hence electric field strength is 0. Get it, kids? Just like that. Yeah. Anyhow, draw this so we can go forward, please. And if you have any questions, let me know. Now, kids, going to the next is this one. If it's negative, obviously it will be flip flop. Nothing really changes except for the direction. So as you go to the right, the negativity decreases, and then as it approaches another negative charge, the negative potential increases like that. Which means that if I draw these two, one's going to look like that, the other one is going to look like this. And if you combine both of them, the net result of both of them is going to be like that. Which basically means if you draw a tangent right here. You draw a tangent right here. It's going to give you a horizontal flat line, which means electric field strength here is zero. And the reason is because right in the middle, because these are repulsive fields, right in the middle, you will see electric null point right here. Any questions, please let me know. All right, very good. Okay, now going to the next. Cool. Now, the next is basically electric field strength graphs. Now, in electric field strength graphs, the important point is that you would not be able to basically draw any electric field strength graph if you do not understand the net potential graph. For example, in the first one, we drew a graph like this. You can verify from the thing that you drew earlier, like that. Then in this one, we had a graph like this. In this one, we had a graph like that. Wait, let me just move it to the center, like that. Now, first one, you guys need to understand that electric field strength is the negative potential graph or negative potential gradient of this, which basically means if I draw a tangent right here, you might see that this tangent that I've drawn is of negative gradient, which means that it will translate into a positive maximum potential. So, which means that here you will have a maximum point. At this point, you have again a negative gradient, but it's quite small. So, this will translate into the positive minimum electric field strength. So, it will be somewhere here. And then if you draw, if you see here at the last point, it is also a negative gradient, but then it has a positive maximum value. So it will come back to this. So this will translate into something like that. Is it clear, kids? Any questions? Please let me know. If you do not understand something, please let me know.
Sir, I don't get this.
Okay. First of all, let me tell you one important rule. Okay. If you ever see a line like this, okay, going up, that is basically a positive gradient. Do you understand that? If a line is going down, then that is a negative gradient. Is it clear?
Yes,
Okay. What do you see right here?
it's going down, so negative gradient.
Negative gradient. We know by the definition of electric field strength, when we wrote it here, I specifically mentioned that electric field strength is basically. Where did I write that? That's not fair. Somewhere here. I said electric field strength, also known as the negative potential gradient. Do you understand that? Which
Yes.
basically means if the gradient, electric field strength, is basically negative potential gradient, right? This is what it means. Now, if the gradient comes as negative gradient itself, so negative and negative sign will cancel out. What will you get? Electric field strength in positive value. Understood?
Yes.
So a negative gradient will give you a positive value of electric field strength. A positive value of gradient will give you a negative value of electric field strength. Get it?
Yes.
Okay, now let's go back. Now, uh, in this one, you have yourself said that the gradient here is negative, which means you will get positive gradient, positive electric field strength, right? So, and why am I calling it maximum gradient? Because as the line is more slopier, the gradient value is higher. So the magnitude is the maximum, but because it is negative value of gradient, we'll get maximum positive electric field strength. Is that clear? Yes, Adam. Okay. A maximum value of electric field strength can be drawn, let's suppose, here, because it's higher, right? Get it? So if I
Yes.
say this is point A, then this is point A. Then at point B, you might see you have a negative gradient, but it is not as slopey as before. So obviously, electric field strength will be the minimum in magnitude, but because the gradient is negative, so electric field strength will be positive. Get it?
Yes.
So that means B has to be the smallest value, but positive value. Understood?
Yes.
Right in the middle. Then if you check the last point, the gradient here is negative, which basically means that the electric field strength has to be positive. And because the line is very slopey, which means it should give you the maximum gradient. Is it clear?
Yes.
So maximum negative gradient will give you maximum positive electric field strength. So it will go back to the maximum side. We call that C. And we'll see. Understood? Like that. Always remember
Yes.
this. Which means if I just join this using a curve, it would look like this. Let me draw B here. Okay. Is that clear?
Yes.
Very good. Now, similarly, we're going to look at this part. Now, in this one, again, I'm going to draw some lines. Abu Bakr, get ready. I'm going to ask you this one. Here, at this point like this, and this point like this. All right, kids. All right. So, Abu Bakr, what is the gradient of the first point A? Can you please tell me? Yes, Abu Bakr. Are you there? Negative. So the gradient is negative. Is it maximum or minimum? Maximum. It is negative and maximum. So which means electric field strength will be positive and maximum. So I'm going to put it right here. So this is point A, positive and maximum. Now, yes, Samir. The second one, please. B. What is the gradient? Go on, please. What does a flat line in a gradient means? What does the flat line mean, really? You don't know? That's bad. Khadija, can you please tell him what is the flat line? Khadija, Zainab, what does a flat line mean? A horizontal gradient, basically horizontal line, Samir and Khatija, basically means that the gradient here is zero. So electric field strength has to be zero. So at this point, B must touch the zero line. Get it? Then what is this gradient? Positive or negative? Can you tell?
Which one, sir?
The last one, C.
Just see. Mm, mm,
A line going up
Increasing.
is no. A line going up is positive or negative. I just told you here. Oh my goodness. That's bad. Yes, please. It is beta positive gradient. If the line is going up like this, it is positive. It is going down, it is negative. Do you understand that?
Say it.
So that means it is positive gradient of maximum value. Because it is a positive gradient of maximum value, that means electric field strength now will be negative and maximum because electric field strength negative gradient. Do you understand that?
Yes, sir.
Okay. Which basically means that now our point C will be in the negative region and at maximum value. So if you draw a curve, it's gonna look like this. Do you guys understand that? And electric field strength basically touches the x-axis here. So this is basically the null point because here the electric field strength is zero. Understood, kids? Like that. Anyhow, the negative signs are simpler. The same way, they're just opposite. So first of all, you're going to draw tangents like here at this point and this point. Yes, so let's mark them A, B, C. Yes, Abu Bakr, the first one, please. Gradient is positive and maximum. Very good. So electric field strength will be negative and maximum. So we're going to put it here. Yes, Samir, B, what is B?
Sir, zero gradient.
Zero. So the gradient is zero, which means that electric field strength is zero.
Hmm.
And then Zainab, C, please.
Gradient is negative and positive Emax.
Gradient and positive maximum electric field strength. So it will be like here. So now you got to make it like this. Oh, my bad. Sorry. Is it clear, kids? Any questions now? Please let me know. अब बकर बस तुम्हारी जान छोड़ दूंगा मैं टेंशन ना लो 1.5 घंटे की क्लास है इट्स 1.5 hour तुम्हारी वजह से मैं जल्दी खत्म कर देता हूँ हमेशा so anyway so we're done here inshallah when we see each other next time we are gonna then work out some questions about it almost all this this chapter is almost finished, so only some questions are left. So I will see you then. Have a nice day. Bye.
Okay, Allah Hafiz, sir.
Okay.